Question 8 opens with the word prove. In fact, every part of this question has a prove or a disprove in it. So here we have to show every step of working. You're not allowed to skip two things in one go. This has to be a full explanation of what's going on. And this is actually reflected in the mark scheme. So the first thing we're asked to do is prove that this function has no turning points. Whenever we see turning points, we should be thinking differentiate, set it equal to 0. So we've got y equals x cubed plus x plus 5. Prove no turning points. So the first thing to do is to work out exactly what we need to do. We need to find dy by dx. dy by dx equals, we get 3x squared plus 1. So multiply by the power, reduce it by 1, and this one just turns into a 1, and the 5 disappears. What we need to do now is show that this is never 0. So we have a couple of options for this. We could use b squared minus 4ac to get no roots. We could complete square. I'm going to use the completing square method. You could use the discriminant if you want to show that this has no real roots. But let's use completing the square. So this is, in fact, we don't even have to. As x squared is greater than 0, could use discriminant if you want. As x squared is greater than 0, 3x squared plus 1 is greater than 1. And if we know this is always greater than 1, 3x squared plus 1 is not equal to 0. It implies dy by dx is not equal to 0. It implies no turning points. We could do this in exactly the same way using b squared minus 4ac, our discriminant, to show there's no roots. Or we can use this, which is just an algebra argument. Or you could use completing the square. That's another option. So this is a proof. What we need to be able to do is go back and read this pretty much either way. We've got no turning points, therefore derivative can't be equal to 0. We know that this can't be equal to 0 because it's got to be greater than 1, and this is the derivative, so we know it can't work. For the next bit, we're asked to disprove by means of a counterexample or otherwise. Sum of 3 prime numbers is always odd. If they give you in the question a hint by means of a counterexample or otherwise, I would stick with the counterexample. It means you could solve it in another way, but let's stick with what they suggest. So we just need to find 3 prime numbers that don't give us a sum added up, it's odd. So if we go with like 3 plus 5 plus 7, that immediately gives us 15, which is odd. We just need to find one that doesn't work. Actually, we're going to go with 2 plus 3 plus 5, because this gives us 10. Disproof. So because 2 and 3 and 5 are all prime numbers, and they add up to 10, not odd. This has been disproved by counterexample. We found one method, or one combination of numbers that don't fit the thing we were asked to prove. For C, we're asked to prove that no single digit natural number is both prime and square. Now there are loads of ways of doing this. The first one is by exhaustion. So no single digit number square. That's what we're asked to prove, and in the question it gives a single digit. So this means we could test them all. We could test 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9. But that takes quite a long time. What we're going to do is we're going to look at just the square numbers. We've got 1 and we've got 4 and we've got 9. There's no point at looking at 2 because we know that 2 isn't a square number. Not prime? We actually defined 1 as not prime. 2 times 2, not prime. 3 times 3, not prime. We need to use the word exhaustion here, otherwise you don't get any marks. Is both square and prime. Actually, we can take this a little bit further and look very carefully at what happened here. All of the square numbers are made up with something else. So 4 is made up of 2 times 2, 9 is made up of 3 times 3. In actual fact, no number is both prime and square. Because if it's square, it's automatically made up of 2 things multiplied together. And if it has 2 things multiplied together that make it up, it can't be prime. So in this case we've just proved enough, which is the single digit ones, but it is actually true in general.